Good morning, I'm Alessandro Umbrico, a researcher at the National Research Council of Italy. I present a joint work with other colleagues of the Institute of Cognitive Sciences and Technologies entitled A Mind-Inspired Architecture for Adaptive HRI Assistive Tasks. Social robots are supposed to support humans in a variety of common situations. To effectively achieve their goals, robots should be aware of the social context and adapt their behavior accordingly. Assistive robots, in particular, should interact with human users characterized by specific health needs and therefore requiring personalized and dedicated assistance. This kind of robots should integrate a number of heterogeneous capabilities that, from our point of view, can be well supported by artificial intelligence technologies. However, the effective realization of these capabilities and the integration of related AI technologies into a uniform control approach represent an open research issue. In this regard, we have started a research effort aiming at proposing a cognitive approach to the integration of AI technologies for the synthesis of continuous robotic assistance. Koala is the name of a recently developed cognitive approach, and here you can find some links to works showing the general idea, its implementation, and some experiments. As a first result, taking inspiration from cognitive architecture, Koala proposes smooth integration of AI knowledge reasoning and planning to allow a robot to internally build knowledge about an assistive context and dynamically synthesize suitable actions. While these AI technologies are suited to synthesize flexible and personalized assistive behaviors, they lack of the reactiveness needed to cope with interaction dynamics that are crucial in many social assistive scenarios. Focusing on dialogue-based interaction, we have thus introduced AI natural language understanding and learning techniques in order to support these dynamics. In particular, taking inspiration from the dual process theory, we have extended Koala and defined a mind-inspired architecture as the result of two parallel but intertwined reasoning processes working at different abstraction levels and with different timescales. So here is Miriam, the mind-inspired architecture we have developed. A reactive reasoner encapsulates machine learning and natural language understanding techniques to realize a faster reasoning process, which is in charge of the dialogue-based functionalities needed to interact with a user and dynamically adapt robot interaction modalities to user feedback and features. A semantic and planning reasoner encapsulates knowledge representation and planning technologies and realizes a slower reasoning process which is in charge of personalizing robotic assistance to the specific needs of a user and guiding the reactive process toward the achievement of assistive objectives. Although the two reasoners are general purpose and can be adapted to different domains and application objectives, in the following we describe the functioning of the overall system by taking into account a cognitive stimulation scenario. In this scenario, the assistive robot is supposed to reason about the cognitive impairment of a particular user, identify a suitable set of exercises that fit his or her cognitive impairments, and then administrate these exercises through a dynamic, engaging, and natural interaction. From System 2 perspective, an ontology models cognitive areas of an assisted person and interaction preferences. Also, the ontology characterizes cognitive exercise in terms of the effect they have on the model cognitive areas of a person. Given this ontological model, the robot knowledge is built from user profiles specifying the functioning levels of the model cognitive areas. Knowledge reasoning mechanism processes this knowledge to infer cognitive impairments of a specific user. They are matched with the ontological model of known exercise in order to identify suitable stimulation actions that address the detected impairments of a user. Then this knowledge is further enriched with interaction parameters that fit user preferences. A very simple example is the volume level of the robot. The outcome of the reasoning process is given as input to the planning component, which synthesizes a personalized stimulation plan as a temporal sequence of exercises that are online dispatched to System 1 for the actual administration. Execution feedback notifies System 2 about their successful or failed administration, And according to this feedback, System 2 can eventually adapt the stimulation plan through the planning. From System 1 perspective, the reactive module defines a set of contextual variables that influence the construction of the dialogue between the robot and the user. These variables are incrementally refined according to the exercise administration requests dispatched from System 2 and to the feature extracted from users' utterances through the natural language understanding component. As we will show shortly, features like personality insights or user intent are used to dynamically structure the dialogue and to decide the way robots communicate with a user. In general, the reactive model dynamically learns an action selection policy based on the defined contextual variables. A key aspect we have considered to support social compliance is the use of multiple communication channels. Following a human social behaviors when communicating, we have here focused on a verbal channel based on robot utterances in natural language and a non-verbal channel based on robot expressions. Let us consider as an example of dialogue for the administration of a stimulation exercise. Define the word exercise in this case. Verbal and facial expression of the robot are set according to the detected user intention and responses. So here we can see, for example, that in case of wrong answers, the robot reacts by assuming a said expression and by encouraging the user to try again. Otherwise, in case of correct answer, the robot reacts by assuming an happy expression and by encouraging the user to try with a more difficult exercise. As the dialogue goes on, the contextual variable of the reactive reasoner are continuously refined and additional variables like personality insight and current mood can be inferred and thus considered to better adapt robot reaction and responses. As an example of use of personality insight, we have here considered the level of extraversion of a user as a parameter for deciding robot reactions. In case of users with low extraversion, a robot would assume a reassuring attitude. In case of high extraversion, instead, the robot would assume a challenging attitude. Again, this is just an example. The reasoning capabilities of the developed architecture are general and can be extended at different levels of abstraction by, for example, adding contextual variables at System 2 level or by refining the ontological model at System 2 level. To conclude, we have shown the general principles of a novel mind-inspired architecture based on the dual process theory, integrating two parallel reasoning processes working at different levels of abstraction at different timescales. At the current state, we have a first prototype of Miriam implementing the described structure and integrating the mentioned AI technologies. Future works will particularly focus on the development of user profiling procedures and on the deployment on robotic platform in order to support experimental evaluation with real users. That's all for my presentation. Thank you for your attention.